title of our presentation is Jaw Dancing American Style, a way to teach English rhythm. I'm Ian Wilson, and my co-authors are Donna Erickson, Tim Vance, and Jeff Moore. Let's start by talking about what is American English rhythm. Well, traditionally, differences in language prominence patterns have been described as a difference in timing. For example, French with its syllable timing and English with stress timing. This paper is motivated by the simple observation that for all languages, we speak by opening and closing our mouth while phonating with our vocal folds. And the result is a syllable, and an utterance is made up of a series of syllables, which in articulatory terms means a series of jaw openings and closings. Syllables are organized into phrase units. Languages differ as to which syllables get prominence. Here are jaw tracings of Japanese, French, and English sentences. Notice for Japanese and French, the top one and the middle one, the largest jaw opening is at the end, but not for English. Japanese and French are edge-strengthening languages, in which the final and optionally initial word receives phrasal stress, as described by Suna Jun in Prosodic Typology, a two-part Oxford University Press book. For other languages, like English and German, each syllable in the utterance receives a certain amount of prominence, with the largest prominence being assigned to the nuclear stressed word or syllable, usually the last content word of the utterance. This slide shows electromagnetic articulometer EMA recordings of the sentence, "I saw 5 bright highlights in the sky tonight." In this utterance, sky has the largest prominence and is perceived by listeners as the syllable with nuclear stress. Notice also that the amount of jaw displacement after the prominent syllable sky is reduced. An acoustic consequence of increased jaw displacement here is increased F1 and decreased F2, given that the vowel phonemes are kept constant. Here you can see a scatter plot of F1 by F2 for one English native speaker's vowels in the words sky and night. In 6 repetitions of the sentence, "I saw 5 bright highlights in the sky tonight." Ovals show 95% confidence intervals. The higher values for F1 for sky agree with the increased jaw opening for that word as opposed to night. This also agrees with the stress being placed on sky and not the sentence final night. Here, the top half of the figure shows the waveform and jaw displacement patterns of the native English speaker. The bottom, those of a Japanese speaker producing this English sentence. We focus here on the jaw displacement patterns of the final phrase, "sky tonight." Notice that for the native English speaker, the largest jaw displacement is on sky, but the Japanese speaker of English has a larger jaw displacement on the final word night, which is in accord with the rules of Japanese prominence. Largest jaw displacement is sentence final for that. We study Japanese speakers here because of the differences between English and Japanese mentioned above, and because we have access to a large number of speakers. We investigate 3 questions in this pilot study. Can teaching jaw displacement patterns help L2 learners change their jaw displacement patterns to those of the new language? Specifically, can they learn to open their jaw on the nuclear stressed item in an English sentence? What is the best way to display the jaw displacement patterns? And can we see the effects of jaw training in terms of changes in formant frequencies, specifically the first and second formants? Participants were 20 EFL students at a Japanese university. They were recorded individually in a quiet room. And at first, they were given the general instructions that you can see in the slide here. The students were then asked to read the English sentence, "I saw 5 bright highlights in the sky tonight," and record their voice using Pratt software. They were allowed to re-record if they made a word error or were not happy with their recording, but very few needed to re-record. One of the questions we wanted to answer was, what is the best method to show jaw displacement patterns, jaw tracings, or bar graph representations of syllable prominences? So in order to assess this visual type of information, students were divided into 2 groups, a jaw tracings group and a bar graph syllable prominences group. Group 1 was shown samples of continuous jaw tracings made from EMMA recordings. Here on this slide you can see the instructions to Group 1, exactly as they saw them. Step 2 at the top was, now look at this picture of jaw dancing, not American style, for this sentence. The group was shown this actual non-native speaker's version at the top, and then step 3, they were asked to look at the picture of jaw dancing American style for this sentence, native speaker's version at the bottom. At that point, they were told to try to make your first big jaw opening on 5 and your biggest jaw opening on sky. And then they were asked to record their voice again using their new American jaw dancing rhythm. As for Group 2, they were shown syllable magnitude bar graphs, where the height of each discrete bar represented the measured amount of jaw opening for that syllable. The lowest jaw tracing for Group 1 and the largest syllable magnitude for Group 2 represented the point where the jaw was most open for the ah part of the I diphthongs in this utterance. In order to assess the degree, if any, of an effect from the dancing instructions on the production of nuclear stress, F1 and F2 measurements were made of the ah vowel in the two words sky and night, before jaw dancing training and after jaw dancing training. Just like Group 1, Group 2 was shown an actual non-native speakers version at the top and an actual native speakers version at the bottom. Now let's look at some results. The results for both groups combined together are shown in scatter plots of F1 by F2 for the final content words sky and night in the final phrase of the utterance. The left graph here indicates that before training, the F1 by F2 values were not differentiated for the two words. The 95% confidence interval for the vowel in sky is completely contained in that of night. And there was a large degree of variation in the production of the vowel in night, orange color. The right side graph shows that after this brief training, there is slightly more differentiation for the formants. This table again shows the combined results of both groups together. We see the F1, F2, and F2 minus F1 values of the ah part of the I diphthong of the two final content words, sky and night, for the combined groups before and after jaw dancing training. The numbers in italics imply increased jaw opening after training. Notice the general tendency for the nuclear stressed word sky to have higher F1, lower F2, and thus lower F2 minus F1 after training compared to before. Higher F1 indicates more jaw opening, while lower F2 can indicate lower and more back tongue position. A smaller F2 minus F1 is to be expected for a stressed low vowel in English. Erickson, in a 2002 Phonetica paper, discusses the fact that even stressed high vowels have more jaw opening than unstressed ones. Now we get to the results for each group separately. Once again, the numbers in italics here imply increased jaw opening after training. For both groups, we see an increase in F1 for both sky and night after training. And for both groups, we see a decrease in F2 only for sky after training. F2 minus F1 ends up being lower after training, but a greater degree lower for sky than for night. A two-sample t-test with Bonferroni adjusted pooled variance p-values shows a significant difference, p equals 0.011, in the values of F2 minus F1 for the nuclear stressed word sky. These changes in formant patterns suggest that Japanese learners of English are indeed paying attention to jaw dancing and are opening their mouths more for both words, but especially for the nuclear stressed word. As for the question of which jaw dancing training was a more effective visual tool for the Japanese learners of English, the results suggest that the learners were perhaps better able to do American English-style jaw movements when they were trained with jaw tracings rather than the syllable magnitude bar graphs. The two graphs at the top show formant scatter plots of Group 1 before, on the left, and after, on the right, training. The two graphs at the bottom show the pre and post training results for group 2, the bar graph group. For both groups, formants of the two words are not clearly separated before training, but after training there is a clearer separation for group 1, trained with jaw tracings, than group 2, trained with syllable magnitude bar graphs. A two-sample t-test with Bonferroni adjusted pool variance p-values shows a significant difference, p equals 0.032, in the values of F2 by F1 for the nuclear stressed word sky, but only for group 1, not for group 2. This suggests that jaw tracings may provide better guidance to jaw dancing than syllable magnitude patterns. So, discussing the results then, it seems that, at least to some extent, Japanese learners of English can quickly learn to change their jaw displacement patterns to those of a new language. And our results suggest that they learn to open their jaw more on the nuclear stressed item in an English utterance after jaw dancing training, as evidenced by increased F1 and decreased F2 on the vowel in the stressed word. As far as which jaw dancing training is more effective for Japanese learners of English, the results from this study suggest that jaw tracings may be better than syllable magnitude patterns. Japanese learners may have interpreted the syllable magnitude bar graphs to indicate they needed to increase intensity on syllables with larger magnitudes. However, since intensity analysis was not done because microphone distance was not controlled for during the recordings, this is a topic for a future investigation. The results of our paper also suggest that approaching prosody through kinematic training may be as effective or even more so than the more traditional method of instructing Japanese learners of English about nuclear stress in English. But future work needs to be done to test the relative effectiveness of kinematic training versus cognitive training by giving linguistic instructions, or versus training with intonational patterns. Jaw dancing applications can be extended, of course, to other language learning contexts, for example, English speakers learning Japanese. A recent study based on acoustic and articulatory EMMA data reported at last year's 33rd meeting of the Phonetic Society of Japan that English speakers of Japanese tend to transfer their first language lexical stress patterns to their second language, their spoken Japanese, especially when the Japanese word is an English cognate. For instance, in the sentence aka pajamada, they are red pajamas, even English speakers who are relatively advanced in L2 Japanese tend to reduce the first and third syllables of pajama. Preliminary work with jaw dancing training using syllable magnitude patterns suggests that jaw dancing training indeed helps learners of Japanese to avoid making stressed syllables followed by reduced schwa-like vowels. This figure shows results for one English speaker of Japanese before and after jaw dancing training. Notice that before training, the three large colored ovals at the top, the middle syllable ja had distinctly higher F1 and F2 values than the other two syllables, indicating a lower, more fronted vowel for ja than for pa and ma. After jaw dancing training, the F1 by F2 values of all three syllables clustered together in the black circle at the bottom. Thus, it seems that this American English speaker reduced the overall amount of jaw movement differences between vowels after training. English speakers, especially teachers of English, perhaps tend to open their jaw more in order to speak more clearly, so jaw training may help these teachers improve their spoken Japanese. Another point is that maybe syllable magnitude training is better for English speakers of Japanese, while jaw tracing, on the other hand, is better for Japanese speakers of English. The rationale is that Japanese may not necessarily have a concept of what an English syllable is, but most English speakers do. Patterns of syllable magnitude to English speakers may indicate information to them about how small a syllable is, which will lead them to reduce the amount they open their jaw. Jaw dancing training may also help other language learners, for example, French learners of English and vice versa. These language learners face the same problem in that English learners of French need to open their jaw less, except for at the end of an utterance, and speakers of French learning English need to open their jaw more on stressed items and less on the following reduced item. In conclusion, then, is jaw dancing effective? Japanese learners of English change their jaw displacement patterns to a more English-like pattern of increased jaw displacement for nuclear stress, as evidenced by the increase in F1 and the decrease in F2. Interestingly, Japanese learners may perform better after being trained with jaw tracings than with syllable magnitude bar graphs, which is interesting because it's more complex continuous data winning out over simpler discrete data. In future work, we need more speakers and more sentences. We'd like to do a parallel experiment with English learners of Japanese. We'd like to do some EMMA and video studies to directly measure the jaw before and after training and to determine the extent that the concept lower jaw equals greater prominence generalizes to all other vowels. Future work may also elucidate more differences between high and low proficiency second language speakers' jaw movements. Finally, it's obvious that most language instructors don't have access to specialized equipment like EMMA, but jaw tracings and syllable magnitude patterns reflect the stress patterns of an utterance, so it's possible to draw pseudo-jaw tracings based on phonologically derived metrical grids, and one could use those for jaw dancing training. One could also use a video camera for tracking of the jaw. Another method coming soon is an international network program called Exploring a New Technology for Measuring Speech Rhythm. This project is a collaboration between 3 researchers at the University of Southern Denmark, Haskins Laboratories, Yale University, and Nanjing Normal University. Finally, we'd like to acknowledge that this work was supported in part by 2 Kakenhi grants, grants in aid for scientific research from the Japan Society of the Promotion of Science. We also greatly appreciate the helpful suggestions we got from 4 reviewers. Thanks.